Hello, hello. I'm teaching a class online, first semester calculus, engineering calculus, and I was just putting up a review of taking the derivative of the product of two functions, something like this. So if I have, let's say, h of x, like that, and that's equal to, let's say, two functions that are f of x multiplied times another function. Okay, and we're assuming that they have the same derivative and everything. I'm not sure why that's that way. And so what I'd like to prove is that the derivative, which is like a h prime, is equal to the f prime of the first function times the second function. Yeah, plus fx times g prime of x. That's what I'd like to prove. Okay, let's see how we might do that in a more rigorous fashion. So let's give an example, for example. For example. So let's say I have h of x, and it's made up of, let's say x squared plus 1 cubed times g of x. Well, I don't want to do g of x. I'll put something, let's say x to the fourth. Okay. So according to that, then to find the derivative, first I'll take the derivative of this guy. See? And that's going to be called, that's called the chain rule and also the power rule. So first from the very outside, I'm not sure why that does that. Let me see. The outside. Sure. Let's see if I can multiply that out. Let's see. Okay, it'll make that multiply full screen. Okay. So now h prime. So what I do is the 3 comes down. That's x to the 2 plus 1, right? And then you subtract 1, that's 2. Now I have to take the derivative of the guts, which would be times 2x, right? Then I'm going to leave g of x the same. So what I'm going to do is put this like this. So I'm going to have, so then I have plus, right? Okay. Plus, right? And then I'm going to have the rest of this thing, which is pretty hard to read. The way I have it drawn here. Let me clear that up. It's not very clear, is it? Let me start over. So I'm going to go like this so that I have f of x. So that now let me go back and start with h of x, which is the product of it. If I want to take the derivative, then I put that apostrophe there, meaning that it's the derivative of h of x. And then first I'm going to take the derivative of whatever f of x is, and then I'll leave that guy alone. Okay, and then I'm going to add, then I'll leave f of x alone, and I'll take the derivative of g prime of x. That's how you do the product of two rules. So you can see here, then I got the plus sign from right here. Yeah, and I brought it down over here, that's a plus. I brought it right here, plus. And now I'll leave f of x alone. Well, remember what we're assigning here is f of x is actually going to be equal to this guy, this whole thing here. And then g of x will be equal to this function right here, see? So now I'm going to leave f of x alone. And now when I leave f of x alone, it's just going to be what it is. In this case, it's x squared plus 1 to the third power. But then I'll take the derivative of that, and that's supposed to be to the fourth power, see? So then you bring 4 down, and then you have x, and you have to subtract 1 to the 3. Let me go back. That doesn't look too good. Yeah, and that's the function, so that for any x, I can generate the slope of the product of those two functions, right? If that makes any sense. Let's see if we can prove it more rigorously. So what I'd like to first sustain is that instead of having f of x and g of x, I'm going to let u stand for f of x, and then I'll let v for g of x. Okay. Then in general, I know that if I'm talking about a change of u, a little change, that means a little change from where it was. Well, that's going to be af of x plus a little change in x minus f of x. That's really, if you look at that, This is a U, by the way. Get rid of that there so it looks. And go back. Let's make it a little neater. U. Okay. And of course, I'll have a change in V too, which would be G of X plus a little change in X minus where it used to be. And that was G of X. See, so those are rate of changes of those two things. Now, what I'd like to do is let's talk about what U and times V would be. Okay, so if I talk about U and V, right, I'm going to talk about, well, the U times V in this case, we're going to say what U is equal to, right? And so, and then we're going to have also, we want to know like the change, a little bit of change of the product. So that's going to be equal to U plus a little change in U. Now, you notice that the U and the change of U and the change of X, if the change of X goes down to 0, so does the change in U. I'll show you that more explicitly. So then what we have is UV, and then I have V plus a little change in V. You see it? Now this, if I wanted it, now that's going to be minus, that's the change in UV, so minus where it used to stand, so that's going to be U times V. Or you can't see it too well, so I'll get over here so I can clear that up a little bit. So this guy over here, this was G of X, right? And then I have to subtract U times V. That's the actual change of the product of those two things. So I'll show you that the total change in U times V is going to be this times that, right? Which is just U times V, right? And then the other one, this times that, will be plus U times let's go back, just we'll make that a little better, U times the change in V. Right now I'm going to do that one, and that's going to be V times a little change in U. And then finally at the very back here, I'm going to have the change in U times the change in V, and then minus UV. But that's kind of handy because this guy here will subtract out with this guy, right? So that what I have now would be the change in U times the change in V equals U times the change in R. I'm just copying it down, plus R times the change in U. Okay, and then that's going to be plus the change in U times the change in V. That's what I have so far, right? And let me show you how that looks like maybe geometrically. So suppose that I have a rectangle, something like this. Okay, and let's suppose I do something like this. Alright, I'll do something like this. So that I'll call this U and I'll V, and you can think of this as the area of U times V, right? And then this is going to be a little change in V, see it? And this is going to be a little change in U. You see that? So, you know, this is a change, this is a little change in V. So this will be U times a change, a little delta. Delta means change. We mean change, delta V, right? And then just make sure I put this clear up this so that you know that this means a change. Go back and then change in V. And of course this one would be V times a change in U, see it? And so and over here we're going to have the change in U times the change in V. Now if you take a look at and you add up those total areas, you can see that the UVs, right, they subtracted out from here and here. And then what we had here was look, U here, so I can go like that. You see it? Oops. And that's going to be this guy right here, see it? So that's UV, and then the first term is this guy. That's well, that's this guy here, right? That's a V. Yeah, and then this guy is this area here. You see, so that the last term is this term, and then this term is the V. du. So the total change is represented in the area of that box, which is the change in uv, right? Would be the change of all the individual areas, and that as summing up the product of those, the sum of those areas. So let's go to that. So the next trick is that I'm just going to take the change in u times v, see, and I'm going to take that and I'm going to divide it by a change in x. And this is so I can start to get the actual derivative. So we want to see how the numerator changes with the unit change of the denominator. For unit change in x, it's a little x movement. How much does the uv change? That's really what a derivative is. So then we have like that, and then I'm going to go on the other side. I'm just going to write what I have. So I have u, and then I have delta v. That doesn't look too good. Oops, u. Then I'll have delta v. See, and then I'm going to have that over the change of x, because I change it on this side, and then over here I'm going to have v. You see, and then I have change in u, and that will be over the change in x. Yeah, and then finally over here, what I have is I'm going to have the last part of it. You see right here, which is I'm just going to leave it like change in u times the change in v. It doesn't matter where I put this in, one of the change of x here. You know, the definition of where you're going to use limits, and that's a rigorous way of showing that the limit of a ratio, like rise over the run, or du, dv, or du over dx, is really how you determine it. So I'm going to take the limit. This is a definition of as delta x goes off to 0, see, of u, the change of uv, right, over dx, okay, over change of x, and that will be equal to, now since there's no change in x on u, I can put the u here and let the limit go like through to the delta x to 0. That's a property of a constant in front of the one I'm interested in. So then I'll be, and what's left here is a delta v over delta x, see it? And now I'm going to do over here, and that's going to leave this out. That means the v will be out here like a constant, and this is going to be limit as a change in x goes to 0 of the change in u over the change in x. Now this other guy is a product. And the interesting about limits is they can distribute through as though it were like a plus sign, like a times b in parentheses b plus c, where you can distribute the a through there. And so I can actually write this one as the limit of the change in u over the change in, well, it doesn't matter. I can just say the change of u, right, as delta x goes to 0, and that's going to be times the limit as delta x goes to 0, yeah, and then what's going to be left here is the change in v over the change in x. Now, since this goes through here, you can see that there's going to be no change as delta x goes 0, because u, well, there will be change because u also goes, if delta x is going to 0, then certainly delta u is going to 0. So we can say that this whole term here goes to 0, which makes that whole thing 0. So the way we can write this as something that looks more neat, I can say that this is now substituting back where u and v, right? So I can say that this means that the derivative of the change in u times v over, see, I changed it to dx because they're differential now because I took it out to the limit. So this is supposed to be a u and a v. Well, it's really what's up above here. So let me just clean that up a little bit. Okay, let's go here. Okay, let me go here. Okay, now, so what we got going here is really that's standing for the derivative, which is the same as, well, we can call it the same thing as taking, now we can call it h. I'll put that thing means h. Or if you, well, I'm saying h of what? Well, that was going to be instead of f of x, instead of u times g of x, which is, remember what I let these things equal right here, see it? So that's going to be equal to, and then this is going to be u times, yeah, and that's going to be the change in v. Oh, well, I know what u is. Let's go back. I'm calling u f of x, remember? So let's call that f of x. Now, and then this guy, v, stands for g, right? So I can call this g prime of x, which is what this term means here. That's the definition of a derivative. That is a definition of, here I just replaced h. Remember, h was originally up here, see it? So I replaced it. When I replaced u and v, I put h. Now I'm trying to show that this is the case right here. I'm actually trying to show this guy here to be the case. So that's all right. Now I got my plus sign in here, and now you can see what I have over here is u, and u is, well, I actually didn't do this one up here, right? So that's okay, doesn't matter, because that one's saying now I'm going to take, this guy right here. And v, we know that v is equal to g of x, right? And u, so this would be f prime of x. And then there's v. And what is v? G of x. And that's what I try to prove. I hope that helps. Okay, thanks.